of understanding the band structure between them. Okay? All right, so let's talk about more than one atom in the unit cell. More atoms in the unit cell. So far we've only considered how many atoms in the unit cell? Yep, one. What happens when we add more? Yeah, I think so. When we add more. Okay, we're still going to go back to our 1D hydrogen chain because it's an easy system to understand. We're going to consider a 1DH chain where we include 2 H atoms in the unit cell. Okay, so that's our system. We have to have 2 atoms in the unit cell. Here's my unit cell. What's this length? It's 2A. We could call it A. But we're going to call it 2A because it's double the length of what we've used in the past, right? Okay. So now an important point. Our unit cell is a length of 2A. Okay. So if we were considering a molecular system, how many hydrogens would be in this unit cell overall? Yeah, 2. We had a molecule. What would our orbital diagram look like? Yeah, dash, dash. How many MOs? 2. How many AOs going in? Yep, 2, 1, an s orbital for each hydrogen. What's this bond? Yeah, that one. Yeah, if I drew a picture like this, how should I shade this guy? What about that one? Okay, how do I fill this thing?
1, 2.
Yep. There we go. I hope to God you were bored of this by now. Yes, we're going to just keep kicking that thing till it comes back to life. Okay, so we have a solid though, right? What we want to do is we want to consider for our chain, what do the block functions look like at the zone center and the zone edge? So since we have a solid, let's consider what the block functions look like at the zone center. What's my value of K at the zone center? Yep. and zone edge. What's my value of k at the zone edge in this case? Yep, it's pi over 2a. Good work. Okay. For the sigma bond, because now we have two sets of orbitals we have to consider here, right? For MOs that we have to consider, because now we have two atoms in there. Pi over 2a.
Are we going to do pi there?
No. If I do pink, will that work to show the difference in the unit cells? So like, that's okay for people? Okay, the first one, how should I shade that in? Well, remember, do we change phases here? No shading at all. We're good to go. What you are describing, pi over 2a. Yep. What's going to happen? So this one's not shaded. What should happen here? Yep. What about here? Yep. For the sigma star, again, we have our unit cell. Okay. Here, in that first unit cell, remember, we're dealing with the sigma star, so how should I shade this thing? Yeah. One should be shaded. Like that, right? Because this is the sigma star. Same thing here. Okay. At the zone center, how should I shade the next one? Yeah. What about this guy? Yeah. Okay. For pi over 2a, how should I shade this? It flips, so where should I fill, left or right? Yep. What about on this next one?
Right.
Okay. So now what we're going to do is we're going to write out what type of character these things have. Top set of crystal orbitals. Bonding, anti-bonding. This one?
Yeah, are you asking within the unit cell or are you asking?
This one's anti.
So it's like
Between the unit cells. But what about here? What about, let's say I call this guy 1, 2, 3, 4. Okay, it's bonding between 1 and 2, right? What about 2 and 3?
No.
Okay. What about 1 and 3? Okay. Yeah, it's non-bonding between 1 and 3. Or do they have the same sign?
No.
Right, so they still see each other. It's further away and there's not much overlap, but they still see each other.
Wait, so are we calling seeing each other overlap or none?
Oh yeah, we're talking about overlap. What'd you say, Lily? No, this one is anti-bonding. I'm sorry.
Oh.
Did I say non-bonding?
Yeah, you did.
Oh, I'm sorry. Okay, this is anti-bonding.
Is 1 and 4 non-bonding?
No, 1 and 4 would still be anti-bonding.
How about 1 and 5?
1 and 5 would be bonding.
What is the limit?
There is no limit because electrons, I mean, now, realistically, does 1 see much of 5? Or does it have much overlap? No, it's pretty far away. But they still have bonding overlap between them. So now we're saying bonding between unit cells. Here. Missing words, letters. And bonding, anti-bonding between unit cells. Okay, now let's consider for the sigma star. What type of overlap between the unit cells do we have here? Yep. What about for that guy? Okay. What do you think we're going to do next? Band structure. Let's plot that band structure. I don't know why I capitalized the B, but that's what I did. Energy on our Y. What's our x-axis? Yep. We're going to go from 0 to what?
I over 2A.
Yeah.
Sorry, what is K again? Is something vector?
Wave vector.
Okay.
It's also counter of symmetry.
Okay.
But it's called the wave vector.
Okay.
Yep, think back to that wave function that we covered. It's just changing phases, basically. Okay, now, MO diagram. We had 2 AOs. How many MOs came out? 2. How many AOs do we have in our unit cell? So how many bands do we need to draw? 2. We're going to have 1 for that sigma type interaction of the molecule and 1 for the sigma star. Okay, let's plot out this one first. Okay, at the zone edge. Yep, bonding.
Low energy to high energy.
Yep, it'll do something like that.
So it's not as drastic as sigma, for it is 1.
Wait,
Yes,
so
it's not as drastic. We're going to talk about why in a minute.
So it's not like sigma.
Yep,
Wait,
it's meant to be more like that, but
It's
not.
like it's closer to a D than a D overlap than a sigma overlap.
Just you will get the answer to your question in a minute. Yeah.
So bonding between unit cells would be intracellular bonding?
Sure. We can call it that. Yeah.
Yeah, so intracellular bonding.
No, not all the time. Okay, you guys are getting to something that we will make sense in a minute, and I sense your frustration and anger, but you're gonna feel silly in a minute. Okay? Yeah, I don't know. I feel like a moron like 8 times out of the day, so I don't know. I just have no ego at this point anymore. Yeah, that I don't have an ego. Oh no. Do you want to know? Do you know what they call what? Do you know what an expert in the field is? It's something that somebody has failed 1 million more times than a novice has even tried. That's what an expert is. So all your professors are morons who have hit a wall so many times. And they know it. Yeah, you don't get a PhD necessarily for being smart. It helps. You get a PhD for being persistent. Tenacious.
Get your persistent degree in
Yeah. And I'm not going to lie, being smart helps. Being lucky is even better.
I know.
Okay. Let's look at these two. Now, zone center for this one. Looking at it, what would you say? Oh, it's water downstairs. Yeah. Okay, back to this thing, guys. Where's this going to lie? High to low. And now, how does this rank in terms of like anti-bonding?
Higher than number.
Yeah.
I don't think it has the best.
Yeah, it's got really, it's high energy, right? So yeah, really sucky. So it starts up here. Now, let's look at these two. Okay. Yeah, they are similar, right? Now, what if I just shifted my unit cell to there? They're degenerate. They're the same thing. Because this actually extends infinity that way and to infinity that way. These two are the exact same thing, just shifted by the unit cell. Yeah. So now, what's this plot going to look like?
Oh.
There we go.
It's a duck.
Yeah, it's a duck. Yeah, duck beak. Now, next question. Where's my Fermi level in this system?
I assume it's a very.
Yep, Katie,
They have bills.
What's the difference?
what are we missing?
Wait, so well, the Fermi level, but the
Yeah.
bottom one is okay.
Yes.
I thought we had more.
Okay. Nope, we don't have any more to draw because here's bond number one, band number 1, band number 2. So where's the Fermi level? How many electrons are in this unit cell? There are 2. Each band holds how many electrons? So where do I need to fill this? Yep, the beak.
Yeah.
Bills,
It looks more like a
What is the
Hershey
difference
kiss.
between a beak and a bill?
the shape and the function.
Okay. Can I erase this part? I'm going to ask some questions now that Joe and Aiden, all those questions you were asking all relate to this. And I know you wanted to jump on it, and that's good because you sense something. Your intuition's telling you something here, and you're right.
All right, let's go.
Or
First.
you know something's wrong with this, or something looks weird about it, right? Yeah, that's the best kind of divine correctness. How is this different? Than our unit cell containing only one H atom. So how is this really different? You're right, it's not. It isn't. I'm going from 0 to what? Uh-huh.
Oh.
0. Now let's say we were doing it for drawing a band structure for the system that had 1 atom in the unit cell. What range do I go to?
0.5/8. Oh.
Okay, what about, and then what does the band structure look like? Yeah, like that. Now, where's the dead center here? Yep, this is pi over 2a, which is weird in itself because we've actually increased in real space, right? So you're doing 2 steps forward in real space, but what does that mean you're doing in reciprocal space? Half a step backwards. It's
Don't think too hard about it. Just look at the math.
yeah, yeah.
That's what I'm doing.
So really, what we're doing is we're flipping this.
Wait, so is that supposed to look exponential then?
And it's meant to, but it kind of folds out that way. It's meant to be a little different. But what we're really doing is just folding this portion back.
Onto itself?
Yep. And we would get, if we increase the unit cell size. This is called folding back the bands.
Did you mean to draw that like linear and then start curving?
No, not really.
So it's supposed to
Just a horrible job of writing that. Okay, now K. I know, Aiden, you asked this a little bit ago, but what is this thing called? Yep, it's a wave vector. Because we're traveling through momentum space at this point that operates in reciprocal space.
So to repeat what you said, that little U thing that was formed was by you said expanding
Unit cell. Yep, so we expand the unit cell. This portion just folds back onto itself. And we really don't get any new information, right? Okay. The band is just folded back. From our 1 atom unit cell. We're going to